Hello, in this video we're going to look at differential equations, our final application of integrals. So let's solve the following equation. Y squared plus 5y plus 4 equals 0. Well, a quick factoring will tell us that we have y plus 1 and y plus 4 equals 0, which gives y equal to negative 1 and y equal to negative 4. There we go, our two answers. So when we're solving an equation like this, our answer is a number, y equals negative 1 or y equal to negative 4. But what if we were to solve an equation like this? Well, notice, this equation has a derivative in it. And in this case, we'll solve for that derivative. So we could move the 4 over and we would get 2 dy dx equal to 8x squared minus 10x minus 4. We could divide both sides by 2, so dy dx would be equal to 4x squared minus 5x minus 2. But we don't want to just find dy dx. We want to solve the equation, we want to solve for y. We want y equals. Well, to get rid of the derivative, we have to do the integral. So y would be equal to 4 x to the 3 over 3 minus 5 x to the 2 over 2 minus 2x plus c. So to go from here to here, right, we did the integral of 4x squared minus 5x minus 2 dx, which gave us what we have here. But notice, in the first one, when we solved for y, we got a number. In the second version, when we solved for y, we got an equation. And the difference between the first and the second type of situation is this is an equation. This is technically a differential equation. So it's a little different. It's similar to an equation. There's similar methods, but there's also some differences. This above, this one right here, is called a differential equation. In mathematics, a differential equation is an equation that relates one or more functions and their derivatives. So notice there was a derivative in this equation. When mathematicians are studying physical processes, more often than not, a differential equation that arises during the process of modeling or some type of real-world phenomenon. So whenever you're doing modeling, real-world type math, you tend to have differential equations show up, not just regular equations. Now, the solution to a differential equation is a function that satisfies the equation. So we're not looking for a specific number per se, we're looking for a function. We're looking for an equation almost to satisfy the differential equation. I know it's a little bit weird, but I'll show you how this works. Back on this example here, we know these are solutions because if we plug them in, they satisfy the equation. So if you go here and you were to plug in negative 4, well, you would get negative 4 squared plus 5 times negative 4 plus 4, which would give you 16 minus 20 plus 4, which indeed would give you 0. So this checks out. It plugs in because it gives you 0 on the right-hand side. In the same way, we're going to show that this equation is a solution to this differential equation. Well, what that means is we have to plug it in. Now, it's a little tricky to plug in because clearly we can plug the y in on the right-hand side, but we're also going to plug the y in on the left-hand side. So let's find dy dx. So dy dx is equal to, well, this is going to be the quotient rule, so low d high less high d low over the denominator squared we go. Okay, well, that's going to give us, if we expand this, e to the x minus e to the x squared. Minus minus will make a plus, so plus e to the x. And then we're going to get another plus e to the x squared. Oh, that's kind of nice. It looks like these two will cancel. And on the bottom we have 1 minus e to the x. Well, I guess we could expand it times 1 minus e to the x. So that'll give 2 e to the x over 1 minus 2 e to the x plus e to the x squared. And maybe we'll leave it right there. We won't expand it any further or try to simplify. Now let's try the right-hand side. So here we have 1/2 times, we've got y squared. It's a little bit messy. We've got 1 plus e to the x over 1 minus e to the x squared minus 1. Okay, well, let's leave that half out in front. And then let's go ahead and work on that square. That'll give us 1 plus 2 e to the x plus e to the x squared over 1 minus 2 e to the x plus e to the x squared minus 1. So now let's common denominator that. So this will become 1 plus 2 e to the x plus e to the x squared minus, well, we're going to get here, if we were to common denominator that, again, we can maybe just write that here. This is going to be multiplied by 1 minus 2 e to the x plus e to the x squared, 1 minus 2 e to the x plus e to the x squared. So in the top we're going to get negative 1 plus 2 e to the x minus e to the x squared. And the bottom's still the same. Well, we're getting close. Notice we have some cancellation here. E to the x squared is going to cancel, and those 1's are going to cancel. So we're going to get something pretty nice here. 1/2 times 4 e to the x over 1 minus 2 e to the x plus e to the x squared. Well, the 1/2 and the 4 can cancel, giving me just 2 e to the x over 1 minus 2 e to the x plus e to the x all squared. And if you take a look and compare that, well, it just so happens that these two are the same. So we did it. Therefore, y equal to 1 plus e to the x over 1 minus e to the x is a solution. It checks out, because when you plug it in, you get the same on the left-hand side as you do on the right-hand side. Okay, so we found a solution. That was pretty good. But are there more solutions? In the first example, we found two answers, -1 and -4. In fact, when you solve a differential equation, you tend to actually have an infinite number of solutions, and they're categorized as what's called a general solution. So if you remember in some of the other questions, we'll have a plus c. Well, it's not always plus c. Sometimes the c is mixed in with the equation, and in this case, the c is supposed to be in front of the e to the x. So let's see if we can do the same math again, but this time show that this is the general solution to the equation. So we're going to do the same thing, but there is now going to be a c in front. So let's be careful with our math here. The derivative will be equal to low d high less high d low over the denominator squared we go. So that'll give us c e to the x minus c squared e to the x squared. Then we'll get plus c e to the x minus, it'll be plus again, c squared e to the x squared over 1 minus 2c e to the x plus e to the x. Well, there'll be a c squared there too. C squared e to the x squared. Now we have a little simplification here. This will cancel. This will cancel with this. And that will give us the following. C 2c e to the x all over 1 minus 2c e to the x plus c squared e to the x all squared. All right, now let's see if we can come up with the same answer on the right-hand side. So we have 1/2, and then we have y squared, so 1 plus c e to the x, or 1 minus c e to the x squared minus 1. So we'll go ahead and square that out. 1 plus 2c e to the x plus c squared e to the x squared over 1 minus 2c e to the x plus c squared e to the x squared minus 1. Do that same common denominator business we did last time. So that'll give us basically the negative of the denominator. So negative 1, positive 2, c e to the x, negative c squared e to the x squared over the same denominator. Well, we're getting close, because if you look, this cancels with this, and this cancels with this. So we have 1/2 4c e to the x over 1 minus 2c e to the x plus c squared e to the x squared, which is 2c e to the x over 1 minus 2c e to the x plus c squared e to the x squared. And so here clearly, left-hand side equals right-hand side. And we ended up with the same thing on both sides, which means, of course, that it is the general solution. But it's a strange general solution, because it means that y equal to any value of c is a solution. So, for example, y equal to 1 plus 2 e to the x over 1 minus 2 e to the x, this is a solution. Or y equal to 1 plus 7 e to the x over 1 minus 7 e to the x, that's also a solution. Any value of c you put there, any value of c will be a solution. There's infinitely many solutions, which is kind of cool. So let's see if we could find a specific solution. Let's find the specific solution to this differential equation with the initial condition. We're always going to need a separate piece of information if we want to find the specific one of these infinite solutions to solve that c out. So we're told that y of 0 is 2. Well, the general solution is 1 plus c e to the x over 1 minus c e to the x. And we're told that y of 0 is equal to 2. So that means x is equal to 0 and y is equal to 2 is a piece of information that we should plug in. So 2 equals 1 plus c e to the 0 over 1 minus c e to the 0. And let's solve for c. E to the 0, of course, is 1. So this is 1 plus c over 1 minus c. We'll cross multiply to get 2 minus 2c equals 1 plus c. We can move that c to the other side, well, the 2c, I guess. This will give 1 equals to 3c, and that'll give c equal to 1/3. So therefore, our answer would be y equal to 1 plus 1/3 e to the x over 1 minus 1/3 e to the x. That would be our specific solution based on this general condition. So as a remark, we've been solving differential equations all along when we've been working with acceleration, velocity, and displacement. And so actually, the questions we were working on last time, the application questions, are technically differential equations. So let's solve the velocity equation given acceleration is equal to 4t plus 3. Well, remember, acceleration is the derivative of velocity. Or we could write this as dv dt. And so we could rewrite the equation as dv dt equals 4t plus 3. So we have a differential equation. The way we solve this is we do the integral on both sides, so v will be equal to 4t squared over 2 plus 3t, and then we get that c. So v is equal to 2t squared plus 3t plus c. We then use this initial condition that v of 0 is 5. And so we go ahead and say, well, that means t is equal to 0, v is equal to 5. We can plug that in. And so we'd have 5 is equal to 2 times 0 squared plus 3 times 0 plus c, or 5 is equal to c. And so therefore, our final equation, v of t, is 2t squared plus 3t plus 5. This is our solution to our differential equation. And it's the same thing as thinking about it as a differential equation or thinking about it as an integral, an application of calculus. It's all the same thing, but I personally like to think about it as a differential equation because then it's related to solving equations. Now, at this step here, you might be feeling a little bit nervous. How did we go from here to here? I said we just will do the integral. And I guess the integral of this side goes to that, and I guess we know the integral, I guess, becomes velocity, but this might feel a little bit tricky, maybe a little bit unjustified, and I'll show you a justification, another way to think about that line. So what we could do is instead look at it like this. Let's pretend we had dv dt equal to 4t plus 3. And just for fun, I'm going to multiply both sides by dt. So I'm cross-multiplying, or I'm moving up the dt, and I get 4t plus 3 times dt. dv equals 4t plus 3 dt. Now, you might argue that this is impractical, impossible, wrong to move around the derivative like this, but for some areas of calculus, this is actually valid. You can think about the dt as a variable, and you can multiply it over, at least in this context. And so what we then do is we pop an integral sign in front of each side. Just like you could do the derivative of both sides, you're allowed to do the integral of both sides. That is a valid thing. You can always do that. What's the integral of dv? You can think of this as literally the integral of just 1. And so the integral of 1 will be v. Over here, we would get 4t squared over 2 plus 3t. Because, of course, on this side, we're integrating with respect to v, so the integral of 1 is v. On this side, we're integrating with respect to t, so the integral of 3 is 3t. And then we put plus c. So maybe that makes it more clear what we're doing, where we're actually integrating both sides. This has a special name, this technique that we're doing. The technique that we used above is called separation of variables, and it works because the above differential equation is what's called separable. Many simple differential equations are separable, and we're going to focus on these in this course. Well, I guess in this lesson, really. There are many differential equations that are not separable. There are entire mathematics courses devoting just to solving these other types of differential equations. So we're just looking at the simplest ones here to give you just a brief overview. Now, this one here is separable. And what do I mean by separable? I mean you can separate x and y using multiplication or division so that they're all on one side or all on the other. If you look here, if we cross multiply, we'll get a dy, and I'm going to put that y squared in front. And here I'll get an x squared dx. So I'm going to cross multiply. Notice how the x's and y's are by themselves. The y is with the dy, the x is with the dx. I've separated the letters. Well, let's just pop an integral sign in front of each of those. Integral of y squared will be y cubed over 3. Integral of x cubed will be x cubed over 3 plus c. Now we should probably get rid of that 3 to give us y cubed equals x cubed plus 3c. And we could go all the way and solve that as y equals the cube root of x cubed plus 3c. There we have y all isolated by itself, and we've solved our differential equation. Let's solve dy dx minus x squared y squared equals x squared. Can we solve this with the same technique? Well, let's try. I'm going to move everything to the right-hand side first. That's not a derivative. So I have dy dx equals x squared plus x squared y squared. Oh, well, factoring seems like something I could do at this step. So I have dy dx equal to x squared plus times 1 plus y squared. Oh, I think I could do the cross multiplying thing now. So dy over 1 plus y squared will equal x squared dx. I guess it's a little tricky here. I'm dividing the 1 plus y to get it on the side with the dy, then I'm multiplying the dx to get it up with the x. But notice, I now have the y's on one side and the x's on the other side. I've separated the variables. As soon as you've separated them, go ahead and do calculus. Go ahead and do the integral. All right, the integral of 1 plus y squared, that's a little tricky. You have to think about it. What function has 1 plus y squared as the derivative? Well, the answer is tan inverse. So this is tan inverse of y. This is just x cubed over 3 plus c. Now we could take tan of both sides to isolate for y. So y is tan of x cubed over 3 plus c. There we go, we solved another one. Let's try another one. In this case, we have this derivative, differential equation, and we have an initial condition, y of 0 is 1. So that should allow us to solve for the c in the end. Well, let's cross multiply to start. We'll get y minus 3 times dy equals negative x dx. Again, notice I've been able to separate my variables. All the x's are on one side and all the y's are on the other side. So we can do the integral. Y minus 3 dy equals the integral of minus x dx. So y squared over 2 minus 3y equals negative x squared over 2 plus c. Now it's nice to clear that 2 out of the way, so I'd have y squared minus 6y equals negative x squared plus 2c. But I'm not really going to be able to solve for y on its own because there's a y squared and a y. I can't really get a y equals out of this one, unfortunately. But I can use this because this tells me that x is equal to 0 and y is equal to 1. So let's plug that information in. 1 squared minus 6 times 1 equals negative 0 squared plus 2c. So 1 minus 6 equals 2c. So negative 5 equals 2c. And this gives c equal negative 5 over 2. All right. Well, therefore, I have my equation. It's called an implicit equation because it doesn't have y isolated, but that's okay. We have y squared minus 6y equals negative x squared plus 2 negative 5 over 2, which we should probably simplify that fraction. So y squared minus 6y equals negative x squared minus 5. That looks nice. And that's my solution to the differential equation subject to the initial condition. Now, let's try a real-world example here. Suppose you just poured a cup of freshly brewed coffee with a temperature of 100 Celsius, right? The boiling point of water is approximately 100 Celsius, depending on your altitude and your air pressure. And when you make coffee, you want to use nice boiling water, so it's 100 degrees Celsius. Now, the room temperature is 20. It's an approximation, but we're going to go with it. And so we want to think about the temperature of that coffee over time. So let's say the temperature, we'll just call it y for now, and here's t. Well, this is 0. Let's say this is 20. Let's say this up here is 100. What do you think is going to happen to that temperature over time? Try to imagine what that graph would look like. Okay, well, the temperature is going to start off clearly up at 100. But it's going to decrease. Now, here's the question. Do you think it's going to decrease like this, like this, like this, maybe some squiggly thing? Well, let's see what we can rule out. We can rule out the squiggly thing because the temperature is never going to increase. You can't unless you were heating the coffee. So it's certainly not going to be the squiggly thing. Now, could the temperature look like this? Well, maybe straight, maybe down. Let's ask a few questions. Could the temperature ever go below 20? I don't think so. I think eventually, whatever happens here, the temperature is going to have to plateau at 20 because that's the room temperature. Eventually, the coffee is just going to be room temperature. So it could be straight down to 20 and then straight off, but something feels wrong about that. It doesn't feel like it's going to decrease right away, just straight down. And the real question is, initially, does the coffee cool faster or slower than when it's cooling later on? If you think about this for coffee, in the first 5 minutes it cools a certain amount, and in the next 5 minutes it cools another amount. When is it cooling fastest? Is it cooling fastest initially or later on, right? Does the coffee stay really hot for a long time and then drop off? Or does the coffee cool down really quickly and then take a long time to get to that room temperature? And maybe you should try this with a cup of coffee if you're not convinced of the answer. But hopefully you are, and hopefully you believe that the correct answer is this one. The coffee initially cools very quickly as it has a large difference from the room temperature, and then slowly approaches that room temperature of 20. So that's going to be roughly the approach for the coffee. That's the rough graph of the coffee over time. Now, maybe you don't fully believe me on this, or you're wondering, maybe you do, but you say, this, I don't know what this would look like. What would this be as an equation, as a graph? How would I model this? Well, let's try to derive a differential equation to model this situation. And in particular, we're going to make an assumption. We're going to assume that the change in y is proportional. So this little symbol here means proportional. It's proportional to the difference in temperature. Difference in temperature. And what I mean by that is it's going to cool not very quickly when it's almost 20, but it's going to cool very quickly when it's 100, because that difference between the coffee temperature and the room temperature, the greater the distance, the faster the coffee cools. Well, here's what that means as an equation. The derivative of y, the rate at which the coffee is cooling, is proportional to y minus 20, the difference between y, which is the temperature, and 20, which is the room. Well, if we put in a constant of proportionality, if something is proportional, we could say it's equal with a constant. And since it is cooling, we're going to put a negative in there. So this negative here is because it is decreasing in temperature. Now again, let's walk through that. We're saying that the rate of change that the temperature has, the coffee cools faster when it's further away, and it cools slower when it's closer in temperature. So the rate of change is going to be related to the difference between the coffee's temperature and the room temperature. And so if we say something's proportional, we could say it's equal as long as we put a k in there, because you could think, if the mug was well insulated, it might not cool as quickly, or if the mug was maybe made of metal and it conducted the heat, it might cool quicker. I'm sure some of you have your favorite mugs that keep your coffee hot longer, or even like a nice thermos, whereas some mugs tend to get the coffee cool relatively quickly, which maybe is good if you want to drink it soon, but maybe isn't good if you're trying to keep it hot for a long period of time. And so the k will be different in those situations, but the overall graph shape will be the same. So now that we've constructed this differential equation, let's go ahead and solve it. So we have dy dt equals negative k y minus 20. Well, we're going to go ahead and isolate for y by multiplying, and then we have negative k dt. This differential equation is definitely separable because you have the y's on one side and, well, there's no t's. So all the t's are on the other side effectively. We put an integral sign in front. Now the integral of 1 over y is going to be ln So we're going to get ln of y minus 20 negative kt plus c. Now, this is a little tricky here, but you can verify that my integral is correct because if I do the derivative of ln y minus 20, I'm going to get 1 over y minus 20, and the chain rule will be a times 1. So this is indeed the correct integral because we can check it with derivatives. All right, so let's go ahead and isolate for y. I'm going to take e of both sides. So I'm going to take exp of both sides. That will give me y minus 20 equals e to the negative kt plus c. And we can finally move that 20 over to give us y equals e to the negative kt plus c plus 20. All right, well, we clearly have way too many constants here, so we should solve for some of them. We know that y of 0 is equal to 100. So that means t is equal to 0 and y is equal to 100. Let's use that information. So over here we'll get 100 is equal to e to the negative k times 0 plus c plus 20. So 100 is equal to e to the c plus 20. So 80 is equal to e to the c, which means, well, this is a little weird, but I'm going to just leave it here as 80 equals e to the c, and you'll see why in a second. When I go back to my equation here, I have y equal to e to the minus kt plus c plus 20. And I can use exponent rules to write that as e to the minus kt times e to the c plus 20. If we have addition as our exponent, we can turn that into multiplication with the same base, of course. And here I have that e to the c apparently is equal to 80. So it just makes my algebra a little bit easier. I don't actually have to solve for c. I can solve for e to the c because that's part of my equation. So I get minus kt times 80 plus 20. And so my equation would be y equals to 80 e to the minus kt plus 20. Oh, there we go. Now, of course, we don't have k solved for, which means k is going to depend on the type of material and the type of mug you're using. But I'm going to show you on Desmos that no matter what you have for k, you still have the same shape that we actually came up with in our hypothesis. So here we have the graph, and just for reference, I'm going to throw on the line y equals 20, which is actually our horizontal asymptote. So you can see here with k equal to 1, the coffee is cooling, and after maybe it looks like 4 or 5 minutes, it's come down to room temperature. Hopefully your coffee lasts a little bit longer than that, and so we'll make the k value a little bit smaller. That means it's going to conduct heat away from the cup a little bit slower. And if we look here, now it takes probably closer to maybe 15 minutes to come down to room temperature. But in either case, for no matter what you pick for your value of k, the graph here looks remarkably similar to the graph that we sketched approximately. You can notice that it's decreasing, it's actually concave up, and it approaches this value of 20 and it never goes below the value of 20. And so we definitely found the correct differential equation, and we found the correct final equation after solving the differential equation to model our situation with the coffee. Now, as a remark, the above situation has a very interesting history and application. The technical name for this principle is called Newton's law of cooling. Yep, it's the same Newton. That guy was pretty productive. Not only did he invent calculus, but he also found excellent applications for it, including this one. And his law states that the rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its surroundings, which is what we assumed when we assumed that the temperature is going to decrease more quickly when there's a larger gap and smaller when they're much closer to each other. With only the initial measurement, there will always be the extra parameter left in the solution, which is what we found, that k value is still in there. This makes it impossible to predict the actual temperature over time. However, with an additional measurement, say 10 minutes after the coffee has been brewed, this extra information will allow us to solve for the extra parameter, and then we can correctly predict the temperature of coffee over time. which is kind of interesting. If you wanted to find out when you should drink your coffee, you could do the mathematics and figure out the best time to drink your coffee. But I want us to do a bit of a different example applying this law. So let's consider a murder mystery. We have a detective and they're called to the scene of a crime where a dead body has just been found. She arrives on the scene at midnight and begins her investigation. Immediately, the temperature of the body is taken and is found to be 30 Celsius. The detective checks the programmable thermostat and finds that the room has been kept at a constant 20 Celsius for the past 3 days. After evidence from the crime scene has been collected, the temperature of the body is taken once more and found to be 28 degrees Celsius. This last temperature reading was taken exactly 1 hour after the first one. What time did the victim die? Now, if you think about this question, it's kind of intriguing, a little morbid, definitely, but very interesting because the human body, if you know, of course, has a regular temperature. The human body should be, when alive, about, assuming you're not running a fever, 37 degrees Celsius. And so we know that some time has elapsed because the body is now 30 Celsius, and we should be able to figure out the rate of this decrease in temperature because we know the room temperature is 20, we know later it was 28. So maybe we could work backwards. Maybe we could create an equation and we could work backwards, not forwards to figure out when the body will cool completely, but work backwards to figure out when the body was 37 degrees Celsius. Well, let's start at the beginning and do our differential equation. So dy dt is equal to negative k y minus 20. And so it's going to be the same as before, but I'll go ahead and do the math for you. So dy is going to be y minus 20, then equals negative k dt. So we go ahead and do the integral. And we get ln of y minus 20 equals negative kt plus c. So we take e of both sides, we get y minus 20 is equal to e to the negative kt plus c, or y is equal to e to the negative kt. I'm going to split it up right away as times e to the c plus 20. All right, well, let's use our information. We're told that initially the temperature here is said to be 30 degrees Celsius. So let's, this is of course happening at midnight. So let's call midnight our t equal to 0. So we know t is equal to 0 and y is equal to 30. So let's plug that into our equation. So we'll get 30 is equal to e to the negative k times 0, e to the c, plus 20. So it'll give 10 is equal to e to the 0, e to the c, or 10 is equal to just e to the c. So we can plug that information back in, and we'll now get y is equal to e to the negative kt times 10 plus 20. I like to put that 10 in front. All right. Well, we also know that 1 hour, we're told that we have some information. 1 hour later, the temperature is going to be 28. Well, let's use that information. So t is equal to 1, y is equal to 28. So let's see what that gives us. 28 is equal to 10 e to the negative k times 1 plus 20. Move the 20 over, gives 8 equals 10 e to the negative k. All right, this one's going to be a little trickier to solve, but we'll keep working. So 8 over 10 is equal to e to the negative k. Well, to solve for that, we need to take ln of both sides, or convert it to ln. So ln of 8 over 10, ln e to the negative k. ln of e, of course, just cancels out. And so we get negative k is equal to ln. Maybe I'll simplify that to 4 over 5. And so k is equal to negative ln of 4 over 5, which you can check on your calculator, will give you approximately 0.223. All right, so we found our value for k. And so let's go ahead and plug all of that into our equation to get ourselves a nice, beautiful equation here. Y is equal to e to the negative 0.223t. And we have it times 10. Oh, maybe I'll put that in front here. Let's clean that up a little bit. 10 e to the negative 0.223t plus 20. All right. Well, we want to figure out the time when the body temperature was 37. So 37 is equal to 10 e to the negative 0.223t plus 20. All right, well, let's solve for time. We'll move the 20 over to the other side. So we'll get 17 is equal to 10 e to the negative 0.223t. So we divide by 10. 1.7 is equal to e to the negative 0.223t. So ln of 1.7 is equal to negative 0.223t. All right, let's keep going. So t will be equal to ln of 1.7 divided by negative 0.223. So if you go ahead and plug this into your calculator, you should be getting negative 2.379. So what that means is this happened 2.379 hours ago. Let's go ahead and convert this into minutes. So, well, it's 2 hours ago and then a little bit of minutes, so 0.379. If we times that by 60, that'll give us 22.74, or approximately 23. So what it means is the murder happened 2 hours and 23 minutes before midnight, which, if we convert that into a time, would be 9:37 p.m. And we were able to deduce that information just from measuring the body temperature twice, when we walked in on the crime scene and 1 hour later. And that's pretty remarkable that we can come up with an estimation. Now, was it 9:37 or 9:35 or 9:40? The real world obviously has some more things involved in it, and we're making some assumptions here. But this certainly tells you that the murder can't have happened at noon, and it also can't have been just a half an hour ago. This person must have died at least an hour to maybe 2.5 hours ago. And so this gives us a lot of information about the crime scene. You have to piece this together with other pieces of information, of course, as a forensic detective, but this piece of mathematics allows you at least to begin to say approximately when the time of death was. So I want you to take a look at some of these exercises involving differential equations. There's a really neat one at the very end that involves an interesting application of Newton's law of cooling. So make sure you take a look at that one at the very end. And as always, thanks for watching.